Hi, and welcome to a Calculus 1 video where we're going to investigate limits at infinity around asymptotes, and specifically in this video we will look at horizontal asymptotes. Right, and one important thing that we can do before we start is maybe look at what is the definition of a horizontal asymptote. What does it even mean for a function to have a horizontal asymptote? So if I can look at this graph here that I have, and as I look as far to the right as possible on this blue function, and as I look as far to the left as possible, again of this blue function, is my function or graph leveling off somewhere? In other words, we're looking at the end behavior of this graph. So let me change the window just a little bit so maybe we can see it. Negative 10 to 10 is not really talking about end behavior in terms of x. We really want to look at as x is approaching positive infinity and as x is approaching negative infinity. So I'm going to maybe choose a window like negative 100 to 100 for x. Again, although I would disagree, 100 is not close to infinity at all. But I think we'll be able to get an idea for the behavior of the graph as x is approaching 100, for example, as a max. I think we'll be able to see what the function is doing, and we don't have to go out to a million or a billion, etc. And then for y's, and I turned off the x scale. I put that to 0 because I don't need to necessarily see 200 tick marks. I'm not going to use it for counting purposes, so I just turned that off. Then y min and y max, my graph did not look like it went up vertically very far, so I just went negative 1 to 1. Let's see what this looks like, see if it's better. Again, this is not negative 10 to 10. This is negative 100 to 100. And I can see that, in fact, there is some value here where my function appears to the left like it's leveling off at some value, and my function to the right appears like it's leveling off to some value. So I just need to figure out what that value is. One way to do that might be to use our table of values. And again, 100 is not that close to infinity, but 1 million is. It's still not infinitely large, but it'll probably give me a good estimation of what the y value will be or where my function is leveling off. Your graph looks like it's leveling off at about a third. Okay, and then as x approaches negative infinity, or the left side end behavior might be something like negative 1 million. And again, that y value looks like it's approaching negative 1/3. So now the question just becomes, how do I show that algebraically? And that's what we're going to look at in this section. So graphically, it's very important to note a horizontal asymptote is an end behavior. Hopefully you learned that from pre-calc courses. And that means as x is approaching negative infinity, what's your function doing, or where is it leveling off, if at all, and as x is approaching positive infinity. A horizontal asymptote, an asymptote is always a line, so this is a horizontal line, y equals some value. You're telling me it's leveling off at y equals negative 1/3 down here, y equals positive third up there. So let me ask you this question before we go to the algebra. Think about this for a second. In this example, there are two horizontal asymptotes. Could there be one horizontal asymptote? That answer is yes. I can show you what that will look like. Could there be three horizontal asymptotes? Think about it. How could I have three horizontal asymptotes? That answer is no, because it's end behavior. So you only have two ends. You have a left end and a right end. So you have as x approaches negative infinity on the left, and as x approaches positive infinity on the right. So there's no other third option, so to speak. If you have two on the left, for example, you are not a function. So for our functions that we're studying, we will only have two at the most horizontal asymptotes. Can there be none? Sure. X squared doesn't have any horizontal asymptotes. Y equals x squared is a function. It's just a parabola. All right, so let's look algebraically now at this. And we're going to answer this question for A which says find the limit. If the limit does not exist, state D and E, but you also need to state Y. So this is going to be a limit as x is approaching positive infinity. So this will have some type of answer, whether it's infinitely large or whether it's a finite value. Okay, so we will learn the calculus behind all of this later on throughout the semester. But for right now, we're going to look at this a little bit differently. If x is approaching positive infinity, I'm going to argue to you that this plus 2 does not matter. And let me tell you why real quick. If I ask you, what does this graph look like? What does y equals x squared plus 2x minus 3 look like? You should be able to tell me, because of the leading coefficient and because of the highest power, that this is a parabola that opens up. So now I know the end behavior, so to speak, or where are those arrows going as x approaches negative infinity and as x approaches positive infinity. I know exactly what it does. None of this other stuff behind here told me what the end behavior was. They just told me things like where the vertex is or how narrow or wide that parabola is, things like that. So told me all my transformations of this parabola. So I'm going to look at this and say that if I look at just the highest powered term over the highest powered term, I will be able to talk about this as x is approaching infinity. Again, if this were as x approaches 2, well, plus 2 is a big deal if x approaches 2. The other idea here is that as x approaches infinity, if I tell you, hey, you won the lottery, you won an infinite amount of money for the rest of your life, oh, add $2 to it. You're not going to necessarily notice that plus 2, infinity plus 2 is still infinitely large. And I'll show you the algebraic reason of why this works here at the end. So now I'm really looking at, this is going to be the same answer as this limit right here, x over the square root of 9x squared. Now I want you to think about something real quick here. Square root of 16 is 4, right? It is never negative 4. Square root of 16 is positive 4. Square root of 9 is positive 3 and all of that. We had the plus or minus come in when we solved equations, quadratic equations explicitly. But what I do want you to know is anytime you take the square root of a value, you are getting a positive output. Okay? So how can I guarantee a positive output, especially if I have a variable inside my radical here, is I need absolute value. Now, I know that no matter what I put in for x, the first thing that I'm going to do is square it. That's going to make it positive. I will multiply it by 9. That makes it still positive. Take the square root of it, still positive. So if I truly look at the square root of 9x squared, it's actually square root of 9 is 3 and x, and those are in absolute value bars. Now the positive 3 could be taken out. So we could write, since it's in the denominator, using my limit properties, this is the same limit as well, with the 1/3 out front. Okay. Now, as x approaches positive infinity, you're going to be putting a positive value in both of these. So in this case, the absolute value really doesn't affect you. X divided by x, they're both positive. So that will divide to be positive 1. So this would be 1/3 times 1, or 1/3. So the limit of all this is 1/3. All right, now let me show you real quick. I'm going to take this away so I can show you the algebra behind all of this. If I go through this whole problem right here and I take this numerator and divide through by the square root of x squared and this denominator and divide through by the square root of x squared, I will be able to see why this works as well. Okay, so this limit, like we talked about, is 1/3, and it was positive. So let's take a look at B. It's actually the same problem, but now limit is as x is approaching negative infinity. So I'm going to think about it sort of in the same way here. At infinity, positive or negative, this plus 2 is going to fall off. That limit's going to become 0 if you divide through by the square root of x squared. And then this plus 1 also is not the highest power term, so that will fall off. So if I simplify this like we did in the previous problem, now I have limit as x approaches negative infinity. X is in my numerator, but the absolute value of 3x is in my denominator. So I can also still take out that 1/3 if you like that better by the limit properties. So limit as x approaches negative infinity. Now this would just be x over absolute value of x. So if I substitute in a negative infinity for x, my numerator is going to be negative. But my denominator, no matter what, is going to be positive. So yes, x divided by x is 1, but they do not have the same sign. Your numerator, x is approaching negative infinity, so your numerator will be negative, but yet your denominator, absolute value, is guaranteeing that positive, so you're positive. So negative divided by positive will be negative. So this will be 1/3 times -1 or -1/3. And that is actually the graph that I just showed you that we started the conversation with today. So if I go to y equals, I typed in the very original. So even if I look at that plus 2 and that plus 1, so x plus 2 is in my numerator. Square root of 9x squared plus 1 is a quantity, is all in the denominator. And I looked at this graph. To the left, it looks like I'm leveling off here at -1/3. That's what B says. If you look left, right, limit as x approaches negative infinity, you're leveling off at -1/3. And if you look to the right, you are leveling off at +1/3. Okay, here's the good news. I think those are two of the hardest ones. So look at C. If your limit is approaching infinity or negative infinity, you can look at your highest powered term over your highest powered term. Because more simply, if you take your numerator and divide by x and your denominator and divide by x, right, you're looking at limit as x approaches infinity of 3x over x plus 2 over x over x over x. I believe that was -4 over x. And again, as x goes to infinity, 2 over x is going to go to 0, 4 over x is going to go to 0, so we can just simplify that part. So that's why I'm able to just scratch that off. So then 3x over x is 3. And again, if you graph that, you should notice that if you look as far to the right as possible, because x is approaching positive infinity, your function should be leveling off at y equals 3. Okay, so here's another one. Again, as x approaches infinity, I'm not just necessarily looking at that first term though, make sure you are looking at the highest powered term. So in the numerator's case, my highest powered term was my first term, but in my denominator, it's not. Now make sure you keep the sign with the term you are keeping. So as x approaches infinity, I'm really just looking at, if I simplify this here, I have x cubed over -2x squared. These are not equivalent, but their limits at infinity are. So their end behavior, or those arrows, are. It's the same conversation as y equals x squared as compared to y equals x squared minus 5x plus 7. They both look like a parabola that opens up. So both of those end behaviors are the same. Okay? All right, so now this is looking like limit as x approaches infinity. So I'm looking to the right. I'm going to pull out -1/2 and put that out here and see if that helps you. x cubed divided by x squared leaves me with an x. So if I think about this, I actually have negative half of infinity if I kind of think about substituting infinity in for x there. Half of infinity is still infinitely large, but it's going to be negative in this case. Now I'm asking you for the limit, not yet for the horizontal asymptote, so your limit value is negative infinity. We went through question E on a previous video here. So let's just look at one last one. Question F. And this one will also look graphically, so we can just see the graph one more time. So again, if I'm verifying that I'm looking at this limit as x approaches infinity or negative infinity, I'm just comparing highest powered term over highest powered term. X squared over x cubed is going to look like 1 over x. And if you're putting in a really large negative number, negative infinity, so 1 over negative infinity is going to approach 0. And so let's look at what this looks like graphically. All right, so if I go to my y equals and I type in my function, pause the video at any time if you want to try to keep up with typing all this stuff in here. I'll hit graph. Now again, my window, is a little bit different maybe than yours, but what I'm looking for is limit as x approaches negative infinity. So I'm looking as far to the left as I can. Is this looking like it's leveling off at 0? Yes. I can also use my table of values to help me. So as x approaches negative infinity, might be something like negative 1 million or negative 10 million, negative 100 million, however large you want to calculate. And this is saying that the y value for that is negative 1 times 10 to the negative 6. So that's approximating your 0 for you. So again, it's important to note that for this question, we were asking you to find the limit or evaluate these infinite limits. Now let's look at a horizontal asymptote question. Well, if you could do those algebraic limits, you can do these horizontal asymptotes. So the same conversation occurs, but what you're actually doing is you're looking at the limit as x approaches positive and negative infinity of your function. And if you think that there's going to be a different limit from the left and from the right, then you definitely want to separate those out. So since I'm looking at that limit as x approaches positive and negative infinity, I cannot pay attention to the plus 1 or any of the minus 3x minus 2. I'm just looking at the highest powered terms here. So then x squared over 2x squared reduces to 1/2 regardless of whether you're putting in positive or negative infinity. So I believe that the horizontal asymptote, HA stands for horizontal asymptote, would be the equation of the line y equals 1/2. And let's quickly graph it to verify. Okay, so I've typed in my function. I like to double check. And again, make sure you're typing in that original function, please. And if I graph it, again, my window probably looks different than yours because I believe I only went from a y value of -1 to +1. And what I can see is that, yep, my left and my right end behaviors are exactly the same. It looks like I'm leveling off at the same value. If you're unsure that it's your value that you think, you can always go to y sub 2 and say y sub 2 equals 1/2. So is that the horizontal asymptote? Well, that looks like it's pretty much mirroring my left and my right hand behavior, end behavior. So there we go. Okay, so I'm going to look at the same thing over here. I'm not even necessarily going to write down all of these steps here, but if I have limit as x approaches positive and negative infinity, and I'll simplify that in this form here to write down in my limit. So this will be the same limit as negative x. And if I'm putting in the infinities, this is going to be negative or positive infinity, which means it's going to continue to grow and grow and grow, positive or negative. It's just going to keep getting bigger and bigger and bigger. So therefore, there's no leveling off or no horizontal asymptote. Some of you may have memorized this as well from previous courses, where if you look at your highest power term, if the exponents are the same, it's just the ratio of those coefficients. So that was where the 1/2 came from. If the power in the numerator is greater than the power in the denominator, like it is for b, you have none because it continues to grow. And then if your power in the denominator was greater, you had a horizontal asymptote at 0, which is what we're going to see in part C. Now, what I'd like to make sure we know is that e to the 2x is actually just a rewrite of e to the x quantity squared, or e to the x times e to the x, however you'd prefer to see that and work with that. And for now, I'd like to just focus on limit as x approaches positive infinity. The negative infinity will require us to use some L'Hopital's rule that we'll learn later on in the semester. I also talked about, previous to this question, why this was going to be y equals 0, and that was because the power in the denominator with the same base, right? So comparing our highest power term over highest power term, the power in the denominator was greater. So it's most likely going to turn out to be 0. So let's look at why. So again, at positive infinity, I can make the case that that minus 5 is insignificant. I can also use my limit properties to just double my limit so that it's not inside of my limit, maybe making it a little bit clearer of what to do. And then I should be able to see, I'm hoping with relative ease, that e to the x over e to the 2x can be reduced to 1 over e to the x. And then again, I'm only focusing on this positive infinity part right now. So if I put positive infinity in there for x, you have 2 times 1 over infinity, or something really, really big. 1 divided by infinity is virtually 0. So this limit would be 0. In other words, my horizontal asymptote will be at y equals 0. And let's take a look at the graph and just make sure that that is working. Okay, here's the y equals. I'll graph it, and we can see, and again, we'll talk about this as x approaches negative infinity later in the semester. It's also y equals 0, but we'll talk about why. This y equals 0, I can see as x approaches positive infinity. So as I look to the far to the right as possible, I can see my graph is indeed leveling off at y equals 0. So I did verify that horizontal asymptote, and you can use your table of values too. That will also verify it. I hope you found this video on limits at infinity and asymptotes, specifically horizontal asymptotes, helpful, and thanks for watching.